Hello and welcome back. In this video we're going to learn about orthogonal trajectories, which have really cool visualizations. An orthogonal trajectory of a family of curves is a curve that intersects each curve of the family at right angles, that is, orthogonally. So figure 5 shows the original family of curves in blue, the kind of bold blue, and then the less bold black curves are orthogonal trajectories to that blue family of curves. So notice that each black curve, if you follow the black curve, it always hits the blue curves at right angles. So right angles all the way through. And that's true of each member of the black curve family. Always at right angles. Let's take an example in figure 4. So figure 4 shows a family of parabolas. Right? These are a bunch of parabolas with different steepnesses, and some are opening up, some are opening down. They're all going through the origin. This is a whole family of parabolas. And the idea here is that these are just showing a few members of the family, but that this family of parabolas fills up the entire plane. So there's maybe a member of the parabola family that's in between each of these, and there are ones that are even steeper. So what do you think the orthogonal trajectory of the family of parabolas in figure 4 going through 1, 0.5 looks like? So going through this point right here. Oops. Oh well. Okay, I tried to put a point there and apparently technology fail. Oh well. So 1, 0.5. Just try to see if you can figure that out. If you have your notes printed out, try to draw what kind of curve you would think is perpendicular to all of these curves in the family. Perpendicular for every single curve of the family. Alright, well if you drew something that looks like this, an ellipse, going through 1, 0.5, then that would be correct in this case. But, you know, there are many other curves that are orthogonal to all of the blue curves. There are many ellipses that you could draw. Each one of them would be perpendicular to all of the curves in the entire family of parabolas. So the orthogonal trajectories of these parabola curves are ellipses. They're concentric ellipses like this. So our goal in this part of the packet is to try to figure out, given a family of curves, so given like this family of parabolas, for example, to find an equation or a formula or the functions that are the orthogonal trajectories of that family of curves. So from the family of parabolas, find the equations for the family of ellipses. Let's turn to the notes. So in example 6, oh, actually, let me back up just one moment too. So this kind of situation might come up when you're trying to analyze something like heat flow, for example. If the family of parabolas represents the isothermal lines, so the lines where the temperature is constant. So all along this line, if this is a constant temperature, and then all along another line you have a constant different temperature, and so on. Well, then heat is going to flow perpendicular to those isothermal lines. So the curves that you would find out, those ellipse curves, would be the curves along which heat would flow. This also has some applications in physics, like in electromagnetism. Let's turn to example 6, where we have find the orthogonal trajectories of the family of curves xy equals a, where a is not equal to 0, is an arbitrary constant. And figure 5 that we had looked at earlier is showing in blue the family of curves that were given. So this is the xy equals a curves. You might notice it's the it's like the 1 over x kind of family. If you solve for y in terms of x, you get y equals a over x. So it's that family of curves. Those are actually hyperbolas. We don't normally think about them as hyperbolas, but they're like rotated hyperbolas from what we normally think. But those are the blue curves. Those are the blue curves in figure 5. The thick blue curves. So we're going to try to find the orthogonal trajectories of that family of curves. Now, where can we start? Well, for one thing, it would help to know what the slopes of the original family of curves are. Why would it help to know that? Because if we know the slopes of each of the members of the family of curves, of the original family of curves, then we can figure out what the perpendicular slopes would be, right? To get the perpendicular slope, you would take the negative reciprocal of the original slope. That's how you get a perpendicular slope. And then from those perpendicular slopes, we can work backwards to figure out what curves are going to go through those perpendicular slopes. So we'll take this in 3 steps. The first step, we're going to find the slopes of the original family of curves. The slopes mean dy dx. Now to find dy dx, we can take our equation and apply the derivative on both sides with respect to x. We're going to have a little implicit differentiation to do, because here we have the derivative of xy. Well, this y variable is different from the x variable, from the thing we're taking the derivative with respect to, so we have to use implicit differentiation. We have to think of y as some kind of function of x. So here we're going to have to use then the product rule. First times the derivative of the second. The derivative of y with respect to x is dy dx, plus the derivative of the first, derivative of x is 1, times the second, times y. On the right side, we have the derivative of a constant a, which is going to be 0. So notice that a disappears from the picture after we've taken this derivative, and that's an important step. We want to get rid of a, or whatever our constant is, that helps us get the family of curves, right? Without a, it would just be a particular member of this curve. If it were just xy equals 5, that's a particular member of the curve, of the family. But xy equals a, that's a whole family of curves. It's an infinite family for the infinite possible values of a. But now we're getting rid of a from the picture, which is important, because we're going to be shifting from the slopes of these curves into the slopes of the orthogonal trajectory curves. Let's go ahead and solve for dy dx. If we subtract the y over and divide by x, we're going to get dy dx equals negative y over x. So these are the slopes of xy equals a. So given any point on the plane, given any xy pair, any point, we know exactly what the slope of the curve that goes through that point is. But now what we're going to do is figure out what the slopes of the perpendicular or orthogonal curves are going to be. So what are the slopes of our orthogonal trajectories going to be? So slopes of orthogonal curves will be the negative reciprocals of the original slopes. So then we have, let me use a different color here because now we're shifting from one curve to the next curve. By a dx, where we're talking now y represents the new orthogonal trajectories, the orthogonal curves, as opposed to the original y, which represented the original family of curves. So here, this is a shift. Now y is changing its meaning here. So dy dx is going to be the negative reciprocal of negative y over x. So flip the fraction, so we get x over y, and then flip the sign, so negative turns into positive. dy dx equals xy. So this gives us now, for every point in the plane, the slope of the tangent line of the orthogonal curves. Now let's take that, which, if you notice, is a differential equation. So this is a differential equation, a dE that represents slopes of orthogonal curves. In fact, this is one of those kinds of differential equations, dy dx equals a function of x comma y. This is a kind of differential equation that you could make a slope field for if you wanted to, right? And then the orthogonal trajectories would flow along that slope field or direction field. So that's a differential equation, though, as well, and we can solve that differential equation. It happens to be a separable differential equation, which we know how to solve. So let's solve that differential equation to figure out what the equations are for the family of orthogonal trajectories. In other words, find the equations for those light black curves in figure 5. Well, the first step we would want to take is move all the y's to the left and move all the x's to the right if we want to solve this differential equation. Let me keep the green color. Y dy equals x dx. Then integrate both sides. We get y squared over 2 equals squared over 2 plus c. And if you wanted to, you could just box your answer right there. I'm just going to take one more step, which is write y squared over 2 minus x squared over 2 equals c. And I like that form a little bit better. Why do I like that form? Because it reminds me of the hyperbola general form. Y squared over b squared equals x squared over a squared, or minus x squared over a squared equals c, or something like that, or equals 1. In fact, I could divide the c over even to make it even better. But this kind of form reminds me that this is a family of hyperbolas centered at the origin. And that's exactly what we see the black curves in figure 5 being. That's a family of hyperbolas centered at the origin. So there we go. We've figured out from a family of curves what the orthogonal trajectories to that family of curves are. And the steps, again, just to outline them, were first find the slopes of the original family of curves, so find dy dx. Then take the negative reciprocal to get the slopes of the orthogonal curves. And then solve that differential equation that you have, which will give you equations for the new orthogonal trajectory curves. So that's it for this video. Thank you for watching, and see you next time.